So welcome to the pre-recording of a talk in a symbolic numeric computing seminar on avoiding and computing singularities in polynomial homotopy continuation. So the title seems to contradict two activities, avoiding and computing, but I hope that I will make this clear very soon. So here is the outline of my talk. I will spend quite some time explaining the context, what is polynomial homotopy continuation and why do we want to avoid singularities and why also we would like to compute them. Our tools come from numerical analytic, continuation and extrapolation methods. So the problem will be defined in the introduction. Then there is the part where we want to avoid singularities. We want to adjust our step size control, taking into account the location of nearby singular solutions. When we come to the end, so in the last part of the talk, we will extrapolate towards a singular solution. We can avoid singularities, but we can also approximate them. The two problems, the two activities are strongly related. Okay, so what is polynomial homotopy continuation? Well, it's a method to solve systems of polynomial equations, systems of many equations and many variables. Here is an example. We have a system F that we want to solve. We call it the target. We have a start system G, and there is a family of polynomial systems. Here it's a convex combination of the target and the start. At t equals 0, we are at the start system, or more in particular, in the parameter space, in the space of all polynomial systems, we are at that start system G. In the solution space, we are at the solution of the start system. So the start system is typically constructed so that we know the solutions, or we can more easily compute the solutions, or we have already computed. That's essentially it. We have already computed the start solutions, and the homotopy defines solution paths starting at those known solutions and ending at those solutions that we want to compute. So the system is called G, letter G for good. So all start solutions, or at least the solutions we want to start at, they should not be singular. So there is this random constant gamma. So if everything should be real, we would still think and we would still work with complex arithmetic. So that is important. So the next picture here illustrates kind of the schematic of parameter polynomial continuation, where we have a parameter space and we have a solution space. In the parameter space, we move all the coefficients of the systems in the homotopy. If we work with random, sufficiently many random constants, sometimes only one constant suffices, then the singularities, they are not, so any of the t values from 0 to 1, they are not on this path, except probably at the end. So it could still be that the system we want to solve, and that's quite likely, has solutions that are singular. Singular solutions are where the Jacobian matrix, the matrix of all partial derivatives, drops rank. So I will repeat that definition. But this is the schematic. Now, you can already ask, what if these stars here, the singularities, they are very far away from this red line here, but what happens if they get close by? Or how close can they actually get in an actual homotopy? That's a very valid question, and that's actually already part of our problem specification. So these paths are well defined, we assume. So no singularity, no diverging path. So a path is diverging when one of its coordinates goes to infinity. Except we cannot avoid divergence if we start with a system that has too many solutions, too many relative to the system that we want to solve. Then some of the solution paths will have to diverge. So let's not worry about singular solutions on a path, or divergence during a path cannot happen. But still, we are left with a numerical problem. So the path is continuous, but we are computing points on the path. So the interval where the parameter t lives between 0 and 1, that is discretized. So we typically use an adaptive step size control. So we don't chop the interval up in 10 pieces and then start computing the approximations. No, that's not what we do. We try to determine our step size relative to the difficulty on the path. Now, it's an important decision. If our step size is too small, then we will do too much work. It will be inefficient. If we are too large, we will lose track of the path. And the problem with polynomials is that the number of solutions can be extremely high. We can have millions of solutions. So it's in a situation where if we lose the path, we jump on another path. And if you jump on a diverging path, then you will lose the solution that you actually were on track to compute. So this is a very important numerical problem. So why does path jumping happen? Well, you can have that the paths are actually have a very high curvature. They twist and bend. So these are cartoon pictures. So one potential choice for a predictor is to predict the next point at the path using a tangent. Now you could say you shouldn't be using just a tangent, use something better. But this is a cartoonish picture to show that you have high curvature of also points, curves that are close to each other. So the paths can have a relatively low curvature, but you will still jump because they are so close to each other. Okay. Just the context. So solving polynomial systems, there are many alternatives for that, and I will not go into this. Also for numerical continuation, and by numerical here I mean the numerical in numerical analysis. So there are alternatives to numerical continuation, and by numerical continuation here we mean that we will be primarily be using double precision arithmetic as much as we can, and we will be using also adaptive step size control and a predictor corrector method. So three alternatives are, I'm kind of have a sampling here of the some of the papers that I've looked at in the literature. There is interval arithmetic, there is parallelotope continuation, and then there is ball arithmetic. So there are three papers listed here. The second bullet, one can also consider symbolic deformation methods. And actually in the first reference there, the 2009 paper, this is where I actually first read the Padé approximants that were used. So this is a symbolic-numeric computing seminar. So Padé approximants, they're well known and well used in numerical analysis, but they also appear in computer algebra. The third category is on certified homotopy tracking, which essentially doesn't use a predictor. So I list two references here. So the 2013, these methods are already at least 10 years old, but the idea predates this. So this is just a sample. So I noticed in the literature that Padé approximants as predictors were proposed already in 1987, the first paper here. But in that paper, use was the predictor had a quadratic numerator and a linear denominator. It was not the root of the denominator was not used. So the poles of the Padé approximants I found were used in the holomorphic embedding load flow method in the IEEE literature. So I've published in the IEEE, but I do not regularly read IEEE papers. But when I discovered what we were doing, then I discovered that in the electrical engineering literature, tracking paths defined by homotopies, using Padé approximants, taking the poles of the Padé approximant, so the roots of the denominator, into account for the step control, that idea already appears over there. Okay, so here is a theorem that is extremely useful. So our solution paths, they are regular at each step. So the power series or the Taylor series is well defined at each and every point. So the ratio theorem of Fabry says that if you look at the coefficient, and in particular if you look at the ratios of the coefficients, notice again that ratio needs to be well defined. You can't have zero coefficients, otherwise it's not defined. You also cannot have series that stop after a while. But if you have a well-defined limit, then that limit is a singular point, and it lies on the boundary of the circle of convergence. So this ratio of theorem of Fabry is very important in our adaptive step size control, in our a priori step size control. So the proof of the ratio theorem of Fabry is very complicated, but you can see the ratio as the pole of the Padé approximants, and I will explain this on the next slide. So when I teach numerical analysis, I teach Padé approximants, and this is a computation that any undergraduate student can do, although typically it's done with numbers, not with letters. So what we have given is a series here truncated after the fourth power, so we have 5 coefficients. With that, we can make a Padé approximant of 3, 1, so degree 3 cubic in the denominator, a linear denominator. Now, the Padé approximants, they require a normalization because you can divide both numerator and denominator by the same constant and have the same values of the Padé approximants. So typically one normalizes the constant term of the denominator by 1. So we have a cubic numerator, 4 coefficients in the numerator, 1 coefficient in the denominator. So we have 5 unknown coefficients for 5 given coefficients. So one can see that by requiring that the Padé approximant agrees with the Taylor series, one can compute a linear system. So if you solve for the term in T4, so this has to equal 0. Um, And now, why would that be? Well, we have here this cubic denominator. So if we say that the cubic numerator equals the series times the denominator, then this fifth term should disappear. So it's at the end of the series. Then actually you see what the B1 is, and you also see the ratio of two consecutive terms appearing. So the coefficient is C4 over C3. If you are looking for which value of t this becomes 0, so this is the pole, then you have C3 over C4. Okay, so this is also an indication if you are using this in your, if you see the Padé approximant as a function, you better not plug in t equals C3 over C, I mean, you better not indeed plug in C3 over C4. So what this slide also, what this analogy, what this connection with Padé approximants also shows is that solutions at infinity and single solutions, they are kind of related to each other. Some people say that if you have solutions at infinity, do a projective transformation, work with in a projective space, work with homogeneous coordinates. Well, you just then translated the solution, the problem from infinity to having somewhere a highly singular solution that's often nearby. So in some sense, sometimes working with homogeneous coordinates make that your solutions that were singular, that were very far away, all of a sudden come very close by. So one needs to be a little bit more worried about this. Okay, Fabry's theorem is very useful, but it doesn't cover all cases. So here is a case that is not covered. It's one of the simplest cases I can work with, although you could also think of two lines, but in some sense, two lines, when they cross, they have a singular solution as well. But here I found it more pleasingly to display a cusp. We have a very simple homotopy here. There is no series. As you can see, if you would develop a series development, then all the coefficients would be 0 after the after the third term. Okay, avoiding and computing singularities. How close can the singularities be, even if you can avoid them, if you know for sure that they are not there? How many terms in your Taylor series do you need? I mean, we have this Fabry ratio, but how accurate is it? So here are some of the tools in the literature. So there is the row algorithm, which I will be using. This was presented by the paper in Peter Wynn. There is the work of Peter Henrici, an algorithm for analytic continuation. And there are the books of bullet points 3 and 4 here on extrapolation methods. So extrapolation methods are very well developed. And then the last reference is a little bit more recent, already 10 years old, but that actually also gives a more modern view on a very classical field of approximation theory. Okay, in analytic continuation or in numerical analytic continuation, one uses Fourier series. One can compute the series, the coefficients of the series by Fourier type methods. So I will not do this because of the step size. With this slide here, I want to point at the difference with Cauchy integrals. Cauchy integrals around the singularity also allow to approximate. So with the Cauchy integral, we have a good point at the Taylor series, but at the Laurent series, at the singularity, we run around the singularity. And there are integrals that then allow you to locate the singularity. The perspective that is taken in this lecture is the picture above. So we are actually starting from a Taylor series, and we want to decide how many coefficients do we need to know to notice that there is a singularity at 1. Um, Again, sampling points around it, you can compute all the coefficients of the Taylor series, but the question of the step size is important there. It turns out that you need a small step size for the leading coefficients, but then for the coefficients that are further out, you need larger step sizes. So I will not deal with these alternatives to compute Taylor series coefficients. Okay, so that was the beginning, the introduction. Let me now go to the a priori step size control. And how do we actually now compute those coefficients of the Taylor series? Now we have a homotopy, and we can apply Newton's method. We can do Newton's method on power series. So working with power series, when the leading coefficient is non-zero, then you can define an inverse. So working with power series is actually more fun than working with polynomials. So power series, they have inverses. So you can, any method, so if you have a generic or a templated uh, algorithm to solve linear systems over any coefficient field, then you can plug in your arithmetic for power series. And your whatever your favorite linear algebra is, it will work on Taylor series. However, while that is symbolically a great idea, however, numerically, it's way more better to apply linearization. Instead of considering vector of power series, it would be better to consider a power series where the coefficients are vectors. So if we are solving a linear system, and that linear system comes from the Jacobian matrix in the update of Newton's method, then actually we have a first series which has matrices as coefficient, a second series which has the right hand side, and that series has vectors as coefficients, and then we compute a solution. That's also a series that had vectors as coefficients. Again, what good does that do to us? Well, the linearization leads to a blocked linear system. And actually now, as far as coding goes, if you are a programmer, you can take your favorite numerical linear algebra solver and simply plug it in. So you solve your x naught, you solve your first equation, your first block, and then you update. So solving this triangular block linear system is then also very straightforward. Now I'm talking about the convenience as a programmer. What is even more important is that by this way of looking at it, you have a handle on the difficulty of the problem. So it's no longer a black box with overloaded arithmetic, but you can see how the errors are actually progressing. So we did an error analysis of this lower triangular block doublets solver, and you could also see why often multi-precision arithmetic is necessary. If you are applying a numerical solver, you always are in danger of losing a couple of decimal places. So if your D here is, say, 31, so we have 32 coefficients, 32 steps. If we are losing one decimal place in every step, and one that's actually not that much, so we have an error of, say we work with double precision 10 to the power minus 16. After 32 steps, we have lost all our accuracy. So one can make that a little bit more precise. And also here, the convergence radius of the Fabry ratio theorem comes into play. So if you actually assume that all the coefficients in your solution are actually nice 1, 1, 1, so your convergence radius is 1, then actually it might not matter all that much. But still, one needs to be careful. So in the literature, in the paper of Henry Shih, he also warns that the coefficients, the leading coefficients, need to be computed with great accuracy if you want to have some accuracy left in the later coefficients. Here is another motivation for using multiple precision. I will not, so the bottom line here goes through the cost. So if you are computing a solution series, which is in some sense very nice, so if you think about this series, so if you have a convergence radius 1, this looks good, but the exponential, actually, if you would apply the Fabry ratio there, then actually that series actually converges, has a very nice convergence. However, if you want to represent even all coefficients, if you want to be able to represent all the coefficients, then it's still okay to use double precision when you compute the first 8 terms. But so with 16 terms, the last term is already 10 to the power minus 13. So there actually one would already prefer double-double arithmetic, which doubles the machine precision here in the last column. Now there is a cost overhead. If you do quad-double arithmetic, and I will actually not say what it is, except that instead of working with one double, you have a sequence of 4 doubles. And with that, with special arithmetic, your machine precision drops to 10 to the power minus 64. So you have about 64 instead of 16 decimal places. But your cost overhead, you do about 1,000 more arithmetical operations. But there are chips available with teraflop performance, and that allows you to compensate. Now we're still in this part in the lecture on avoiding. So when we avoid singularities, we work in double precision. By default, in my software, I don't compute more than 8 terms. Okay, what is now the framework of predictor corrector methods? With an a posteriori step size control, you check the performance of the corrector. So we predict the next point on the path, and then we run typically Newton's method a couple of times and check whether the corrector converges. If the corrector doesn't converge, you often know that you immediately have to cut the step size. That also reduces greatly the risk of path jumping, by the way. But in general, an a posteriori step size control uses this feedback loop. With an a priori step size control, you will try to avoid, so you will take into account the nearest singularity, and you will already check what is the residual when you take the predicted solution, the y here, the bold y at the new step. If that is too large, you will also cut the step size. Okay, so we typically cut the step size in half. There are still two parameters here. Even if so an a priori step size control does not need feedback loops, but it's always good to do one extra corrector step. But with the two methods that we are using, the location of the nearest pole and the detection of the curvature, we typically do not need feedback. Okay, we use Fabry to somehow get the location of the nearest singularity. We estimate the distance to the nearest path using the information of the Jacobian and the Hessian. So we have this estimate. At the end of the lecture, I will have the slide with the references. So what we are doing, that we're doing n+1 singular value decompositions to get this estimate here. And this estimate also gives an estimate for the step size using the Padé approximant, depending on the degree of the Padé approximants that we are using. Okay, so here is now the summary of our a priori step size control. It's the Newton Padé, or the Fabry Hesse Newton Padé predictor, as I called it. So we have, on the one hand, the step size control from the distance to the nearest pole. So the capital D is the pole distance. And then we have the curvature bound from the previous slide. So we are running Newton's method on this block doublet system. We construct Padé approximants. So we have, for every coordinate, we have a Padé approximant. We take the smallest pole that we find of all the denominators, and that will be multiplied with some beta. So the beta here is some fudge factor, some safety factor, typically at this 1/2. So these are experimentally defined. Sometimes it could be that you could take 0.75, but it's probably not good to take 1. So, and then we compute the Hessians. We run the singular value decompositions to compute the smallest and the largest singular values. I could save a lot with my linear algebra routines. So singular values are typically computed iteratively. So you don't need all of them. So in practice, if you implement this, it's good to know about these options in the linear algebra routines. Okay, so we also stay away from the end game. So the end game, that is then for the next part, for the last part of this lecture, when we can expect singular solutions. Okay, so here is a back of the envelope cost analysis. So there is cost overhead. So we do n singular value decomposition. So n singular value decomposition is cubic in the dimension. So we do n of them. So we have as many equations as unknowns. So we also have the cost to differentiate and to the evaluate. Also the power series computation. So That is where we get the factor n log n from. Or if you forget about the log n, you could say that if you have to solve a system with 20 equations using this a priori step size control, it may cost you 20, a factor overhead of 20. So there is no such thing as something that comes for free, but my advice is use parallel computers to offset the cost overhead. So if you have to track many paths, then message passing on distributed computing is actually the recommended fastest way to run things in parallel. And that was done on a benchmark problem. So there is the area of numerical analytic continuation, the theorem of Fabry that I didn't know, but actually the main practical result for me and was the resolution, the correct resolution of benchmark problems, very large benchmark problems, not large in terms of dimension, but the number of solutions. So the Katsura 20 benchmark is something that I tried to solve for a long time as soon as I was having cluster computers. But there were always path jumpings. And in the literature, so there is Home for PS 2.0 para, where the authors actually report 4 path jumpings in their many runs on Katsura 20. So at the end, I found that 66 solutions has a relatively large condition number of about 10 to the power 7. So you are at risk to lose about half of your working precision in your accuracy of the solutions. So Katsura 21 is very unlikely to be, can most likely not computed with double precision. You may have to use extended precision there. I haven't done this. So there is the other benchmark. So Katsura 20 follows the plane theorem of Bézout. 2 to the power 20 is about a million. If you have 13 cubic equations, you would expect 3 to the power 13, but in this benchmark system, I was using linear product start systems, which is a more fancier way of using the theorem of Bézout. But in those very large problems, and for me this was important, that one can apply this method, and there is cost overhead, but on a 44-core workstation, it is doable. Homogeneous coordinate formulations were also here important. Okay, so then another benchmark system. So there is the cyclic 11 roots. It's a sparse polynomial system. On the next slide, I will kind of give the context, a little bit of mathematical context about the mixed volumes. But here on this problem, and this was not reported in the paper, but here we have the two predictors. We have the step size control coming from the nearest singularity and then coming from the curvature. So around about half of the path, you could think that we have a diverging path. And this is where the Hessian criterion, the curvature criterion, the curvature bound actually forces a very narrow. So that criterion is actually causing havoc. But there is no near singularity. So if you relax, if you remove the curvature bound, then actually you can complete in double precision. So my colleagues at the time, Simon Thelen and Mark van Barle, they had their own Julia implementation, and on the same path with the same start system, same parameter, they actually encountered exactly the same results. So this is here a case where 11, so this is dimension 11, but the polynomials have a much higher degree. So the 10th equation is a polynomial of degree 10. So so figuring out here when you have to up the precision, or when you have to use or kind of relax the bounds imposed on your predictors is actually important here. work still in progress. Okay, in transitioning to the last part on singular solutions, I have to say something about how can you ever be sure to find all solutions. Well, we can compute generically sharp upper bounds on the number of isolated solutions by looking at Newton polytopes. So a Newton polytope considers you consider all the exponents of the monomials with non-zero coefficients. So that's why they are capturing the sparsity. So the Newton polytope of a dense polynomial is always the same triangle. Although you could choose very strategically, of course, your monomials. If all the highest degree monomials are there, then you have a simplex as well. If you have a regular subdivision, so from computational geometry, you have a regular triangulation. If you lift the points and you look at the lower hull, that induces a subdivision. We call that a regular subdivision. The height can be interpreted as the powers of an extra parameter. So you have your polynomials, you consider actually you add an extra variable. You have heights, powers of these extra variable, and that corresponds to a construction that will define homotopies. That's a construction that was also used in the constructive proof of Bernstein's theorems. So here are the two theorems stating that the mixed volume is a bound on the number of isolated solutions. I'm not saying that I'm not defining mixed volumes here, but you could say that if you have a system with random coefficients, as many equations as unknowns, then the number of solutions of that system is a constant, and that is the mixed volume. It doesn't depend on the particular choice of the coefficients. So this is random. So the fact that this mixed volume exists and can be computed independently of the coefficients is not so difficult to understand. If all the polynomials have the same Newton polytope, then the mixed volume corresponds to the volume, normalized so that the linear system has volume 1. Okay, so there are also conditions on where the bound is not sharp, and this is when there is an initial form solution, an initial form system that has solution with all coordinates different from 0. Why is this C star important? Well, if you shift a polytope, you are multiplying with a monomial. So you are introducing solutions with 0 coefficients. But the volume doesn't change if you shift your polytope. So actually this indicates that this mixed volume will allow you to avoid counting those trivial solutions. Now there are stable mixed volumes that allow you to count this. And this is also incorporated in my software, by the way. Okay, so the takeaway from this slide is that if you have divergence, you will notice it with coordinates of your solution paths getting larger and larger, but you will actually also notice it if you look at the initial form systems. So there is a way to certify the divergence. So this is important here. Okay, let me now focus to the case where you have singular solutions at the end. At a singular point, you have the partial derivatives, the Jacobian matrix that's not full rank. So before you attempt anything else, at that point, you may want to detect the value of the parameter. This could also be, in some sense, I talked about the avoiding of the singularities. The singularities, even if they are not on the path, they can be very, very close. So what this Fabry criterion essentially does, it takes into account how close the singularities can get. Now, avoiding is one thing. If you avoid this, then you passed it, and that's fine. What happens if you want to know the location of the problem? How many terms in your Taylor series actually are needed? Okay, let's look at a very simple example. So here is the simplest non-trivial example, that of a monomial homotopy. So a monomial homotopy consists of a monomial and a constant, and a power series. So you can actually write this homotopy as x squared equals 1 minus t. So here is the picture. It's a very simplest non-trivial monomial homotopy, but you could say that if you don't understand this case, so we are here now at one of these two green points, the regular solutions, and we want to detect is there a turning point. Now, by the way, turning points in numerical analysis, they are very nice methods, and that's very well understood. Very good algorithms for it. So I'm not claiming here that I'm solving any important problem, except that I do not want to go near that singularity. So I want to predict, I want to kind of detect already quite far from the singularity. I want to see, can I detect with my Fabry ratio theorem that there is something wrong there. And yes, we can. And actually, under the assumptions of the ratio theorem of Fabry, that means that the coefficients define a ratio for every term. So you have a sequence. So you have no zero coefficients, and your zeros, that limit exists. Then we could show, and this is in our CASC 2022 paper, that the convergence ratio is actually 1 over n, which will allow the application of Richardson extrapolation. So this result was in agreement why Richardson extrapolation worked. It's also in some sense good. So if you have 8 terms, then actually you could kind of say that you have 3 bits or 2 or 3 bits accuracy of your nearest singularity. So this kind of confirms all the millions of paths that were tracked without jumping, without losing any step size, without needing any feedback from the corrector, accurately predicting. That's the good news. So the bad news is that if you want to accurately find where your singularity is, so at the end of the paths it's always at 1, but suppose that you would track paths that have points, that can have points as singularities, you would like to know a little bit better. So you see, even with 256 coefficients, you only have about 3 decimal places correct in your answer, which is not good. Logarithmic convergence, here this picture actually shows it kind of dramatically. I'm actually used to using Newton's method. Do one more step with Newton's method if it converges quadratically, and your accuracy doubles. Here, you do twice the amount of work, you compute twice the number of coefficients in your series, and you only get 1 bit of accuracy. So that's actually the opposite. So in some sense, computing all these coefficients in the Taylor series, this is going to be extremely expensive if you do not know extrapolation methods. So this is again a slide to indicate where the problem that we're currently considering. We have gone past a singularity, and now we're going towards a singularity. So we have the case of a monomial homotopy. Monomial homotopies are very interesting to work with because there is no singularity between 0 and 1. But in some sense, we can always reduce to that case of a monomial homotopy if we have the notion of the last pole. So suppose that this is here the last pole, then actually as you are moving closer to 1, you can actually recenter your coordinates or recondition your homotopy. So this is where also the end game comes in. So at some point you notice that you go closer and closer to 1, and if you are actually going to a singularity, you notice that the step size get closer. So you are at 0.999, and your nearest singularity is no longer this red P here, no longer has an imaginary part. So it's actually 1.000, and then the imaginary part is getting very, very small. So this is the notion of a last pole. At the last pole, that's actually the last singularity before 1. So it's a singular solution at the last pole. We have a rank deficient Jacobian matrix, so it's a value for t. Of all the poles, that's actually closest to the left of 1. So that's the once you have that, you essentially recenter. So here's a very simple benchmark example. So if we are reconditioning, so the last pole, so we could see that the last pole occurred when the path tracker was about 0.956. And then after reconditioning, using 64 decimal places, 64 terms, I'm sorry, in the Taylor series, we have about 2 decimal places correct. But you can kind of see that what matters is actually the imaginary part is already very small. You can improve this with Richardson extrapolation, that you have about 6 decimal places correct. At that point, you can, for example, apply deflation, or you can further also extrapolate on the coordinates. So deflation, which I will not explain, restores the quadratic convergence of Newton's method at the presence of an isolated singularity. So that kind of resolves the singularity. Okay, so this was an example at CASC 22 at the paper. So another benchmark is cyclic 9 roots. That was solved symbolically with Gröbner bases already a long time ago. If you converge to the fourfold root, so it has isolated solutions with multiplicity 4, then actually after you recondition and with 32, not this is still double precision, but I confirmed it in double precision. Here actually we are already so close that extrapolation is not necessary. So you clearly see that the convergence radius is already correct. So we actually get it gives this convergence radius correct to 9 decimal places. Okay, this was actually scheduled for a 45 minutes talk, and it's good that I pre-record this. I can go on here in this pre-recording, nobody to stop me. Now, going past the 2022 paper, going past the critical distance, we can see what happens if we apply better extrapolation methods. So the row algorithm on this very simple example is just fantastic. And the row algorithm needs only 4 terms. So we have applied Richardson extrapolation. That gives about 8 decimal places with 64 terms. If you do repeated Aitken extrapolation, you get a little bit better, 11. But the row algorithm only needs 4 terms. Kind of magic. Not so magic anymore if you understand that the row algorithm actually computes the even ordered convergence of the continued fraction, the interpolating continued fraction, that's called Thiele interpolation. Okay, and I noticed that here is where the slides are slightly out of order. If you run the row algorithm with the last pole, so if you are very close to the last pole, then you see that at 8 terms, so there is, so with the square root there was no other pole, but now suppose that there is a last pole, then you see that if this last pole is quite close, then actually with 32 terms you only get 1 decimal place correct. So the row algorithm is not very effective. But if you get closer and closer to the singularity, so the last pole soon that you drive, and in your rear view mirror you see the last pole fading away. So if your last pole is farther and farther away, then actually the row algorithm will improve and will again give you good estimates for 8, 16, and 32 degrees of truncation of your series. Okay, what can go wrong now? Well, what can still go wrong? So what if you still have a pole close by, but you can't really scale it away? So you are recentering at the origin, but it could still happen that you have this orange Q here. So you have this orange that is close to 1. And then actually, if you apply the row algorithm to this, then you have an error that is still sufficiently quite large, even if you use 32 terms in your series. Okay, I'm close to an hour. I hope that this is not too confusing. So, the first conclusion is that the ratio theorem of Fabry is quite efficient, is quite effective to have a good step size. And that is also, that became apparent in our second study. So if you think about how many terms that you need in the Fabry theorem, then if you want to avoid the singularity, then 8 terms typically suffice. So that in the second part with the logarithmic convergence, it's pretty bad on the long run, but at the beginning you get some bits of accuracy. Okay, there is still an issue with the poles that are close to 1, but to the right of 1 in the complex plane. So because these are not necessarily recentered, we don't really see them because they are at the right of the singularity at 1. Then that is still ongoing work. One could construct Padé approximants with quadratic denominators of increasing degrees of the numerators and extrapolate on the roots of those. These experiments are still ongoing. So I'm 1 hour in, so that's way over time. So there are 3 relevant papers. So I would suggest start with the middle paper. That's the one that is published in SciAm. The other 2 papers, the first one discusses the linearization. It also already pre kind of predicts the application of the Padé approximants. So there is also a Padé approximant in that paper already. So Padé approximants are tools to deal with singular solutions. That's well known. And singularities were the topic of the last paper. So I stop the recording now.